Am I good to go?
Yeah, go right ahead.
Fantastic. Well, thanks a lot for the invitation. This is also my first official Zoom talk, so any technical difficulties, unfortunately, it can probably be blamed on me. And I'm going to be talking. Let's see. Actually, this will be. Can people see my mouse? For pointing purposes. Okay, very good. So I'm going to be talking mainly on a couple papers. The first being some work with Miriam, Jim Halverson, Ling Lin, and the second with Liam McAllister, Mike Stillman, who's a mathematician, and Liam's excellent student, Mehmet Demirtas. And if you have questions throughout, please just go ahead and shout them out. Yeah, I would love for this to be more interactive. So the fun part of the getting the Zoom slides together is you have to rearrange where the little Zoom bar is, where you can see the people, depending on how your slides are outlined. So let me give a quick little summary of the general story, just to keep a roadmap in our heads as we go forward. So our claim, this is from the first paper with Miriam, Jim, and Ling, is that in string theoretic realizations of the standard model, the following three statements cannot all simultaneously be true. And let me say them in a colloquial fashion. I've included some technical statements as well below. The first is, our landscape is a typical vacuum or our vacuum is a typical vacuum in the string landscape. The second is that the effective field theory from string theory is under theoretical, perturbative, and non-perturbative control. And the third is that there are no additional dark gauge sectors. So these are the three statements that we're claiming you get to choose two of, but not all three simultaneously.
Sorry, Cody, just to clarify something when you say the standard model realization in string theory, are you thinking like supersymmetric standard model? What do you mean really?
So the concrete realization that I'm gonna mostly be focusing on is MSSM and related constructions. But I think the general conclusions we're going to draw apply beyond that for the reasons that I'm going to discuss. But yeah, please keep that question in mind and bug me about it as we go through, because that's a really important question.
Okay.
So my let's see. How can we click? Very good. Okay, so the way that we're going to draw these conclusions is from simply trying to get the gauge couplings correct in string theory. And there's a few different ways you can sort of put three statements together into an interpretation. And the way my takeaway, the way I like to think about it, is that this is further evidence that we expect a large amount of dark gauge sectors in string realizations of the standard model. I'll explain what I mean by further as we go along. And also a pressing need for new techniques to work with string theory away from control in the alpha prime expansion at small volumes, and the need for new moduli stabilization schemes. So let me jump into part one, which is going to be expectations from string theory and more specifically F theory. So the string landscape. String theory is the leading candidate for UV completion of the standard model and gravity, but it naturally lives in 10 dimensions. There are a few different choices for these 10-dimensional theories, and in general, they're unique, at least at the two derivative level, up to higher derivative corrections. And so to get an effective 4D theory to match the observation of 4 dimensions from our universe that we see, we need to somehow get rid of 6 of these dimensions. And the way to do that is to wrap up the 10-dimensional theory, to wrap up 6 of those dimensions in some small compact space, which is some Calabi-Yau space or related. So each 4D solution of string theory corresponds to a choice of a compact space, which I'll call X, plus other discrete data on X, which can include flux and branes. Branes you can think about as solitons in the string theory. So the number of ways we can do this is absolutely enormous. So the first thing we must do to achieve such a 4D effective field theory is to select a suitable geometry to compactify on. Throughout this talk, this will mostly mean a good base for F theory. So the first question is just how many different choices of these spaces do we have? Well, some numbers for n equals 1 supersymmetric compactifications, which is going to be my main focus, and I'll talk about that more in a little bit, is that there's an exact lower bound of 4/3 times 2.96 times 10 to the 755 suitable bases to wrap up string theory on, suitable spaces X to compactify on. And Monte Carlo estimates the actual number of these spaces to be around 10 to the 3,000. So we already have an enormous number of spaces upon which to compactify string theory.
Sorry, what do you mean by, how could there be a Monte Carlo estimate? Couldn't the number be infinite?
Yeah, the number could be infinite. What's holding us back from an infinite number is needing to be at finite distance and moduli space. And this is a rather technical thing. But the way that we've understood these bases is by starting from a string theory, a compactification that we understand very well, and then moving around, performing topological transitions, which are within the Calabi-Yau moduli space. And so you can do that until you hit a point at which you would be infinite distance. So at some point you do a blow up in the base B, which puts you at infinite distance. So the Monte
there's
Carlo
no reason.
yeah, sorry.
But isn't there no reason to really believe that you can get from that? Couldn't there just be disconnected families?
Yes, there could be disconnected families. So there could be an infinite number, as you say, but within this class of theories that I'm going to talk about, the estimate is about 10 to the 3,000. My point here is not that it's finite. You know, my underlying belief is that it is, but my point is that it's huge.
Well, fair enough. But I guess my point is more, what if you're going to use this as a starting point to make some arguments, you should also have some reason for us to believe that these are representative, or that this is like the majority or something like that.
Yeah.
Could you make some comments about that?
Yeah, I can within the context. So you know, when I'm trying to make these statements, I am trying to explore the landscape. So I'm going to be working in a particular corner of the landscape where I can actually do calculation. So you can throw out any argument I might make about this being completely representative of the part of the landscape that we can't explore. I can only speculate on that. But the way this works in F theory is that things seem to go very, very wrong if you start to move towards infinite distance, towards one of these possibly disconnected islands where you have so-called 4-6 codimension 1 singularities and other singularities. The effective field theory doesn't make sense. So the general belief is that the field theories only make sense in this web of connected F theory geometries. Clay, does that answer your question?
Yeah, approximately. I mean, I understand what you're trying to do, but I think a cynic might say that this is some tiny subsector of the landscape.
Yeah,
I mean, there is that lurking worry, I think.
That is, and that's actually going to play somewhat of a role, hopefully in a way that's clear as we go along in the talk. And I'll try to speculate on maybe how to press outside of this tiny corner that we're looking in. But there certainly is a lamppost effect in trying to just explore the landscape. And I can't claim that this study is particularly getting around that, only that we're doing our best to explore and seeing what we find and see if we can maybe come up with it.
Okay, great.
So yeah, so these numbers I gave, and thanks, that's a great question. These numbers that I gave were simply for geometries, and on top of these geometries, one also can introduce other discrete data, such as flux, which even further distorts these numbers. So a typical geometry has, you know, something like 10 to the 500 flux vacua, and atypical geometries could be home to as many as 10 to the 272,000.
Cody,
so landscape is absolutely, yeah.
I mean, I would not take these flux vacua numbers with anything but a grain of salt, because they're counting things that are not solutions of anything. So they're counting sort of no scale supergravity solutions of some superpotential, but that has nothing to do with semi-classical solutions of string theory. I actually would say that the right count here is probably order 1 relative to your geometries. So if you say they're of order 10 to the 3,000 geometries, I think that's actually the count of the landscape, as best we understand it today. assuming roughly one supersymmetric solution per geometry. There may not
Which
be
you're
any.
referring to. You're referring to a tadpole canceling W0 is equal to 0
Exactly.
solution.
Exactly, because that's the only thing that actually is solving the equations of motion. Otherwise, it would be like saying, why are you counting Clavier geometries? Why don't you also count non-Ricci flat geometries that are, not solving the Einstein equations? Well, it's just a meaningless count to try and sum those up. There's an infinite number of them. They don't mean anything. But these flux vacua that say Douglas and friends were counting don't solve the space-time equations of motion. They're as meaningless as non-Ricci flat geometries as a starting point to do string theory. So
if we restrict ourselves to solving only for W0 equals 0, then this number, as you say, could be a lot smaller.
Yeah, right. It's basically of order 1 or 0 per geometry. There's no large frequency coming from flux.
Yeah, I'm tempted to This is a really interesting point of discussion, as you know, Sav, because you're the one who's really introduced a lot of these ideas. But I'm tempted to punt some of my own questions to you about it until the end. So maybe I'll end the counting here, and then we can talk about it afterwards.
Okay, good. But I think the good news is you have a huge set of geometries, so it's not like you don't have enough.
We have enough. The news is we have a lot. Maybe the bad news is too many, but
right.
Yeah. So how have we tried to get a handle on this enormous set of solutions so far? There have been sort of two sides to the same coin of exploring and understanding the landscape to the best that we can. And the first is to explore the landscape by just going in and doing calculations and seeing what we find and trying to understand patterns that we see. And the second, which is known as the swampland approach, is to use consistency arguments and mathematical arguments to rule out possible theories based on that. There are emergent patterns from both of these approaches, mainly conjectures with supportive evidence and ensembles with statistics. And today is going to be more of a landscape approach of building things, attempting to solve a problem and seeing what we find. So where can we find or attempt to find our universe in string theory? Well, the first question is, what sort of structure should we introduce at the scale of the compactification? In particular, how much supersymmetry? Of course, there's plenty of well-studied compactifications with n equals 2 SUSY, but these are too supersymmetric to describe our world, which is clearly n equals 0 at low energies. However, as Sav was somewhat pointed out a minute ago, there aren't any metastable compactifications with n equals 0 known at the compactification scale, and there's no strong hints on how they might be constructed and controlled at this point. Not to say they don't exist, but it's not something that we've been able to explore directly. On the other hand, there are theoretical reasons to consider n equals 1 supersymmetry at some intermediate scale, which can be spontaneously broken to then give an n equals 0 vacua somewhere. And introducing some n equals 1 supersymmetry at the level of the compactification improves the prospects of finding n equals 0 vacua anyways, due to stability of the compactification. So I'm going to focus on the n equals 1, the theories that preserve n equals 1 at the scale of the compactification. So where should we look? We have many different options in the string theory duality frames, the two different heterotic theories, type 1, 2b, 2a, M theory, and F theory. And I'm going to focus on F theory for a couple reasons. The first is it's a strongly coupled generalization of type 2b string theory and is more general, so allows us a bigger playground, a bigger landscape to explore. The second is, the reason I'm going to focus on F theory over a lot of the other duality frames is we have a lot of tools to study F theory that are very powerful, namely algebraic geometry and holomorphicity to understand F theory. So this gives us a lot of control and a lot of power in actually probing these theories. So let me give a brief introduction to F theory, which is so far our largest playground to date. All those numbers I quoted before were from F theory compactifications. So it's a solution of strongly coupled type 2b with 7-branes in there in the internal space, and it's geometrized. So I control the internal space via some geometry, but the seven-brane solution is also geometrized in the form of an elliptic vibration, which tracks the data of the seven branes. This gives me a lot of geometric tools to play with, to use to understand F-theory compactifications. So mathematically, well, it's a choice of physical extra dimensions, a space B upon which to compactify 2B string theory. I go from 10 dimensions to 4. And then on top of that internal space B, I choose a Calabi-Yau elliptic vibration, which determines the position and type of seven branes, and in turn determines gauge sectors, matter, Yukawas, all this gauge theory data. So in terms of equations, what I do is after I fixed an internal space B on which to compactify, I just introduce a little bit of extra data, which is an elliptic vibration above this internal space. The way I write it down is in this Weierstrass equation: y squared is equal to x cubed plus fx plus g. X and y are projective coordinates on some variety that I fibered over the base, some P231. And f and g are locally polynomials in the coordinates on the base B. And globally are sections of some line bundles in such a way that the total space is Calabi-Yau. So what this data does is allows me to track the seven branes. So the seven branes are located where this elliptic vibration becomes singular, where the little torus pinches off in various places on the base. And this is given by this discriminant locus delta is equal to 4f cubed plus 27g squared is equal to 0. So whenever I solve this equation on the base for some choice of f and g, I find seven branes. And then the way that the equations behave as I go near the zeros, which is called the multiplicity of vanishing of f, g, and delta, the discriminant locus, determines what type of seven brane I have, and therefore what kind of gauge group I have. And these gauge groups are classified by the Cody classification. So the way that if f goes to z to the a, g goes to z to the b, delta goes to z to the c, I get some seven brane along z equals 0. Z is a local coordinate in the base. And these integers, a, b, and c, determine via the Cody classification what kind of seven brane I have, and therefore what kind of gauge group. So this Cody classification is a classification of degenerations of elliptic vibrations at codimension 1. So in F-theory, what we find is sometimes you get many gauge sectors, even if you didn't ask for them. So for some choices of base, for some choices of extra dimensions that I compactify type 2B string theory on, F and G, and therefore delta, have some non-vanishing multiplicity of vanishing generically. So for all choices of f and g, no matter how I change the coefficients, f goes as some z to the a, g goes as some z to the b, and delta goes as some z to the c, where a, b, and c are non-zero. So no matter how I move around these polynomials, no matter how I move around the seven branes in internal space, I always get the same multiplicity of vanishing. In this case, the gauge groups on the seven branes correspond to so-called non-Higgsable gauge groups because they cannot be Higgsed geometrically. So even if I try to Higgs them, if I try to move around the moduli, I can't. No matter what choice I make, I always get the same gauge group. And the possible choices I've listed here in red. So not every gauge group can be non-Higgsable, but many can. So all the elliptically fibered Calabi-Yau fourfolds lie in a connected moduli space. And that's one way I can understand the possible bases, the possible suitable compactification spaces I have to wrap up type 2B on. There's a sort of minimal set called weak Fano toric variety, or just weak Fano varieties, which do not have non-Higgsable clusters. But as I start to move away from this minimal set, I find non-Higgsable clusters right away generically. So on the right here on this little picture, I'm going to start with some geometry that doesn't have non-Higgsable clusters. It's a weak Fano variety. Now I'm going to start moving through moduli space, through the different bases I have. So I'm doing topological transitions in Calabi-Yau moduli space to start exploring different F-theory compactifications. And as soon as I start to move away from this weak Fano variety, well, I immediately find non-Higgsable clusters. So here I've allowed, this is just a graph of a bunch of these different topological transitions. And I've allowed something up to what we call height 5 transitions. And there are about 4,000 nodes in this graph, and all but one have non-Higgsable clusters. So these are fairly generic. And in fact, in all the ensembles of F-theory bases that we've
Cody, can we just go back one sec? So it's proven that
try.
all elliptic fourfolds are in a connected moduli space?
Yeah, so DiCerbero and Spaldi proved this in 2016. Yeah, that that's right. Yeah.
Mm. Okay.
Yeah. So this
By
is
that
a
you mean they're
generalization.
connected by birational transformations?
Yes. Yeah. So just to comment physically on what can happen is if you have a base and you have 7 branes, you can stack them up enough so that a new modulus becomes light, and then you can Higgs in that modulus, which corresponds to a blow up. That's one such transition. And of course, the other transitions are the resolutions of fiber. So these are the general motions from which you get from one elliptically fibered Calabi-Yau fourfold to another. So just to quote some numbers for evidence for non-Higgsable clusters from ensemble studies. Just in the ensemble that Jim, Ben Sung, and I created, which numbers in thirds in about 10 to the 55. The probability of finding non-Higgsable clusters in such geometries is about 1. It's 1 minus 1.01 times 10 to the minus 755. And in fact, that's a lower bound. So in this ensemble, non-Higgsable clusters are ubiquitous. There's a similarly strong result in the random walk, in the random walks through similar geometries. And then the F-theory geometry, believed to be home to the largest number of flux vacua, has a large number of non-Higgsable clusters. And a typical geometry or a typical gauge group in these, at least these first two ensembles, tends to be large, many factors of E8, F4, E6, and other stuff. So we expect lots of dark gauge sectors. So generally, just from exploring the F-theory landscape in the regime that we can, we have a few expectations. One is that we have many dark gauge sectors further due to non-Higgsable clusters. And the second, and something that I haven't gone into detail about, is that we're going to have many axions as well, since most F-theory bases have large H11, and for each H11, I get an axion for dimensional reduction of C4. C4 is a 4-form gauge field that lives in the 10-dimensional ambient type 2b theory. These are not necessarily problems, but features that can also make for some interesting model building that wouldn't necessarily be apparent from the ground up, from the IR point of view. So I've given you some expectations from F-theory, but what I'm going to do now is I'm going to try to push back on this. I've told you that from exploring in the F-theory landscape, we expect many dark gauge sectors, and I'm going to try to struggle to avoid that. I'm going to say, what can we do to avoid such dark gauge sectors? Can we realize theories that are just the standard model with no extra dark gauge sector stuff? So let's try to do that. Let's try to evade these dark gauge sectors. We have lots of we have a lot of evidence that we should expect dark gauge sectors via these non-Higgsable clusters. But there are geometries in which we can avoid them. These starting points I showed you. These are bases for F-theory that don't have non-Higgsable clusters, where one can engineer pure standard models or MSSMs. These bases, algebraically, are called weak Fano bases, and the condition, the geometric condition, is the anti-canonical bundle of the base dots non-negatively with all holomorphic curves on the base. And a generic elliptic fibration over such a base is smooth. So I don't have any non-Higgsable clusters. So starting out, just writing the convectification and not tuning anything, I don't have any gauge groups at all. So one might imagine that I could tune a pure standard model on such a base. But the challenge of doing so is really a challenge of tadpole cancellation. So even without non-Higgsable clusters, the 7-brane tadpole cancellation on the internal space is the main obstructions. So if I wrap some divisors, some codimine 4 cycles in the base on some cycles WI, these are homology cycles, well, the tadpole cancellation condition for the 7-brane satisfies this equation. I sum over the different cycles weighted by their multiplicities, the number of times I wrap these 7-branes around them. And this has to be equal to the class of the discriminant locus that I introduced earlier, which is 12 times the anti-canonical bundle. So if the visible sector, if I'm trying to engineer the standard model, if the visible sector doesn't saturate this 7-brane tadpole, well, I have leftover 7-branes just as a result of tadpole cancellation. And these might provide extra gauge sectors. So what I want to do is I want to explore these bases and the consequences of tadpole cancellation in the context of some geometry that we can understand very well, namely toric geometry. Toric geometry is very powerful and wonderful because a lot of it is combinatorial. So weak Fano toric threefold, which is the ones I want to study for 4D F-theory convectifications, corresponds to a triangulated reflexive three-dimensional polytope, which I'll call diamond. The reflexive condition is that the only interior point of such a polytope is the origin. You can't see it through this green solid color, but there's an origin inside here. And the dual, defined by diamond circle, it's defined by the, I'll label it diamond circle. It's defined by the fact that all points in diamond circle greater than or equal to -1 with all points in diamond. Well, this dual also has to be a lattice polytope. These have been classified. There are 4319 distinct 3D reflexive polytopes. And each triangulation of it, each subdivision into simplices on the boundary corresponds to a distinct geometry up to some automorphisms. So every time I triangulate one of these, I get a new topologically distinct geometry upon which I can convectify F-theory. So because the number of triangulations determines the number of geometries, the polytopes with the largest number of triangulations dominate this ensemble. And there are two polytopes with 38 points in the boundary apiece, which admits on an order of 10 to the 15 distinct triangulations. So this result is due to Halverson Jim and his student Tian. And because these geometries have the largest number of distinct phases, they dominate the landscape of weak Fano toric varieties in 3D. So now I have some geometries, and I want to start trying to engineer the standard model. So to preserve n equals 1 supersymmetry, to construct the standard model, I'm going to wrap 7-branes on cycles in the space, on codimension 1 cycles. These are 4 cycles. And to preserve supersymmetry, the 7-branes have to wrap effective or holomorphic 4 cycles, which I'll refer to as divisors. So in order to achieve a pure standard model gauge sector without anything else, there are 2 necessary conditions. One is that if I wrap 7-branes on a cycle to construct a standard model, well, I can't have other 7-branes pop up somewhere else as a result of tadpole cancellation that also gives me a new gauge group. That would automatically fail. The second condition is that the cycle upon which I wrap 7-branes to engineer the standard model has to be irreducible. So if I try to wrap the 7-branes on a reducible cycle, what'll happen is I'll end up with a double copy of the gauge group that I intended. So this will also give me another sector, which is unwanted from my original goal. And in toric geometry, these requirements reduce to questions about the polytope and the triangulation. So let me talk a little bit about toric homology. Each point on the polytope represents an effective toric divisor, one of these 4 cycles upon which I can put 7-branes. And these divisors generate with non-negative integer coefficients, all divisors in B. So I have a minimal set of homology classes from which build up all the holomorphic homology classes with non-negative integral linear combinations. The intersection structure is also determined by the triangulation. The edges between the points encode intersections between 2 divisors, and the little triangles, the simplices, encode triple intersections. And all these triple intersections are simply 1. So an effective 4 cycle, a holomorphic one, and its homology class in the base can then be represented by labeling points on the polytope with non-negative integers. And today I'm going to make a simplifying assumption. I'm going to restrict myself to square-free toric divisors. So I could label these points as 2s, 3s, etc. But I'm going to consider divisors that can be written as integral linear combinations of the toric divisors with coefficients 1 or 0. So the data of such a divisor is simply represented by a simplicial complex T on the polytope. I color in some points, and the data of the divisor is completely encoded by the points and the intersections between these points, which is a simplicial complex.
Sorry, what is the physical significance of being square free? I don't really understand what this assumption is about.
There's nothing physical at this point. I'm only allowing myself to study these divisors because they give me a large set in which to do this analysis. So it's rich enough to start to understand some things, but it's also small enough to be tractable where we can really get some control. There will be a more physical reason that pops up in a bit as to why some of these divisors are particularly nice, but really physically you could think of this as me studying the minimal configurations wrapping 7-branes.
Okay.
So remember, the positions of the 7-branes are given by the vanishing of the discriminant locus. And if I'm going to demand the existence of a standard model gauge group, well, this implies the discriminant locus factorizes. I'll get some delta standard model times some residual discriminant. And this residual discriminant, delta prime, is what's going to encode all of the possible dark sectors. So if I find there are no additional gauge sectors, well, the necessary condition for that to be true is that delta prime can't factorize. If delta prime factorizes, I automatically get at least some additional 7-branes somewhere else wrapping individual divisors. And it often is the case where it factorizes to the point where I get additional gauge sectors. In terms of polytope data, I can write down the polynomial defining delta in terms of, I can take the dual of diamond. So I take diamond circ, which is the dual, and I could scale it out. And this scaled out polytope encodes all the data of this discriminant locus, delta. So the discriminant locus is written as some complex coefficient Cm times some monomials of the coordinates in the base. And to tune a gauge group on one of these divisors, well, what I'm doing is I'm setting some of the Cm equal to 0, so I get some non-vanishing multiplicity of vanishing for one of these coordinates. So I have to turn off all the monomials where a coordinate doesn't appear to high enough order. That's how I'm going to tune gauge groups. I'm going to turn off monomials in delta. So let's start small. Let's start with some minimal divisors, these prime toric divisors that correspond to points on the polytope, and start trying to tune the standard model on these divisors. I'm going to do this by placing 7-branes, which is equivalent to demanding some multiplicity of vanishing in the discriminant locus delta. So the fact which we showed is that for a point P in some face S, so this is a face S, if I tune a gauge group on a divisor corresponding to a point interior to that face, well, I automatically get 7-branes on divisors corresponding to all points interior to that face. So in these next slides, the tune gauge group is going to be on some divisor labeled by a blue dot, and the additional 7-branes I get automatically via tadpole cancellation are those labeled by red. So if I try to tune the standard model gauge group on this divisor here, I automatically get additional 7-branes. The way one can show that is the particular monomial I had to cut out was the only, to get some non-vanishing multiplicity of vanishing along that divisor, was the only monomial protecting the rest of those divisors interior to that face. So let me just give some examples. So I can tune on every single point interior to this face. Watch as the blue dot moves around. And I always get some 7-branes on the other points interior to the face on the corresponding divisors. So I'm already in trouble if I try to tune the standard model gauge group on a divisor corresponding to face interior point. Now, I can also try points interior to edges.
Sorry, when you say you're in trouble, so the extra 7-branes you're getting, you're still solving tadpole cancellation, right? Go in the total space. So aren't you making a prediction that if you put the standard model there, you have to have a rich dark sector?
Yeah, that's what I'm finding. I'm trying to push up against that. My goal right now is to engineer pure standard models and study the consequences of them. So in terms of that goal, I'm failing miserably. But yes, I am making a prediction. So what we're finding is that most at least for small homology classes on the toric variety, most choices of wrapping 7-branes will result in additional 7-branes, which could lead to dark gauge sectors and generally do. So if I try to tune a 7-brane on an edge, well, the edge, I get 7-branes on all points interior to the edge, plus all faces that the edge bounds. So since this edge bounds this face, I get even more 7-branes by doing this on an edge. And it's even worse for a vertex. The vertex bounds the face and 2 edges. So I get an absolutely enormous amount of 7-branes. So these small divisors, these minimal ones, don't work so well. So let's start to try to combine them. So these extra 7-branes generally only need be I1 7-branes, which don't carry a gauge group. That's what we were able to prove, but generically they actually do. It gets further enhanced. So to avoid this, let's go bigger. Let's try wrapping the standard model branes on linear combinations of prime toric divisors. Let's try combining these things to try to create one big smooth 7-brane to house the standard model. So I'm going to wrap it on a linear combination of prime toric divisors, wrap the standard model 7-branes. And a necessary condition for no gauge dark sectors, not sufficient, but necessary, is that this divisor that I'm wrapping on doesn't itself factorize. The reason being is that I would get a bunch of copies of the gauge group I was intending to build. What this means is the corresponding line bundle dual to that divisor needs to have more than one section. The way you see that is there's always the hyperplane section, which is the product of the coordinates that would vanish along each component of the divisor. And this is always a section. So you always have to have more than one section. And for square-free toric divisors, so Clay, this gets into your question, we can actually calculate this without any big tools. This becomes a simplicial complex question that we can answer very easily. So that's one reason these prime torics give us, and these square-free toric divisors give us a lot of control. So the number of global sections is given by, let me consider the simplicial complex that corresponds to this divisor. I'm just coloring in the dots and then keeping track of all the lines and simplices connecting the dots. Well, the number of global sections is given by 1, there's the hyperplane section, plus the sum over all vertices weighted by the genus of the vertex. G is the number of interior points of the dual face. So each of these faces has a dual face. And I just count the number of interior points. So it's the sum over all vertices weighted by the genus, plus the sum over all edges, complete edges, not partial edges in the simplicial complex, weighted by their genus, plus the sum over all faces, complete faces in the simplicial complex, weighted by the genus. So the point here is that to increase H0, to get more sections to make this thing not factorize, I need to include vertices with non-zero genus, full edges with non-zero genus, and full faces with non-zero genus, which is already pretty restrictive. And let me show you sort of how that works. So let's look at one of these really big polytopes that gives the majority of the geometries, the majority of the weak Fano toric threefold bases. Well, when the polytope itself is quite big, the dual down here is quite small. So this polytope has 38 points. This dual has 1, 2, 3, 4, 5, 6 points. So it's already small. All the faces of this, which you'd be able to read off from the dual, have genus 1. These faces are dual to the vertices. All edges have genus 0, and only a single vertex, this one down here, has non-zero genus. And remember from my previous slide, we needed non-zero genus. We needed non-zero genus to help increase H0 to make this thing not factorize. So it already looks pretty restrictive. So let's consider these divisors and their corresponding simplicial complexes. Remember, what we need to do to get this thing not to factorize is to include full faces and vertices, because the edges all had genus 0. So I'm just going to draw a bunch of examples. This divisor factorizes because I don't have a vertex or a full face. This divisor factorizes too. Even though I have a full edge here, this divisor factorizes because all the edges have genus 0. So the only representative of this line bundle is x1 ... xn. I guess it's x6. 7 is equal to 0. So this automatically factorizes. Even if I include almost the full face but I omit a point, it factorizes. Even keeping all these and omitting the point in the middle, it still factorizes because these vertices have genus 0. Not a fact you can see by staring at this picture, but just done from the calculation. So finally, if I include a full face, well, the polynomial doesn't factorize. I finally get an extra monomial. Combinatorially, at most a fraction of 2 times 10 to the minus 10 of these square-free divisors on the large polytope do not factorize. So what we're learning is that in order to not have a factorization, which would force additional copies of the gauge group that we were trying to tune, we need to try to wrap the standard model on some big divisor. The divisor corresponding to a full face satisfies one of these properties, but actually it's not sufficient because from tadpole cancellation, we can still have other 7-branes somewhere else. But this hints towards some structure. And the structure that it turns out that works very well is to choose the anti-canonical divisor itself to be the divisor upon which we wrap the standard model 7-branes. This anti-canonical divisor corresponds to a sum over every single Toric divisor. So I take all my points in the polytope and I color them in. I just color the entire polytope, the boundary of it. And this gives me the anti-canonical divisor. So from the simplicial complex point of view, it's one of the most trivial ones you can have. As it turns out, this divisor is a K3 surface in B, and it's always irreducible and smooth. It's actually a promising choice in another fashion. If I tune the elliptic vibration a little bit more, if I choose a particular choice of elliptic vibration by tuning the coefficients in F and G, well, choosing this anti-canonical divisor to wrap gives the exact chiral spectrum of the MSSM with the gauge algebra SU3 across SU2 across U1. So this elliptic vibration in equations just looks like this sort of long thing, but it's encoded in terms of polytope data as well. Oops. These models also have the nice features that the gauge couplings unify in the UV, even though the model is not necessarily a gut. And there are no dark gauge sectors. The other nice feature is this is independent of polytope details. There's one for each triangulation of each polytope. And the estimate for the number of such models is order 10 to the 15 because the largest polytopes in this ensemble have 10 to the 15 triangulations. So I've sort of achieved my goal. I found a large number of suitable pure standard model constructions without dark gauge sectors. There can be other things, but I've achieved my goal. I found some constructions of 7-brane models without dark gauge sectors on 7-branes. So let's refine this a little bit.
Wait, sorry, Cody, before you go on, so
the
data that you're fixing is the geometry and the gauge group. You're not at the moment worrying about things like background flux or the matter spectrum.
Yeah, so there was a little bit of implicit flux in my previous statement. You have to introduce the correct flux to get the chiral spectrum. But what Miriam et al. Proved in a recent paper was that you can always find such a flux for most of these bases. So that's where they get the quadrillion. They actually do introduce the correct flux to induce chirality.
So it's just a massive number of pure standard model compactifications that you find then.
Yeah, it depends. So the key point is no dark gauge sectors from 7-branes.
Yeah.
These things have a large number of axions. There could be vector-like matter as well. But what they were looking for was pure standard models that are dark gauge sectors.
Good.
So let's refine this a little bit, and let's try to compute something a little bit beyond topology. So making this particular choice of the anti-canonical bundle to wrap the 7-branes on gives the exact MSSM chiral spectrum at the level of topology. But what about the gauge couplings? Well, one requirement we have physically is that we need the UV gauge couplings to be large enough, to be able to flow to our measured value in the IR. So an example target is the gut gauge coupling. 1 over alpha is equal to 4 pi over g squared is about 25 at the scale of the compactification. This isn't something we need to hit exactly, but we just can't have gauge couplings in UV that are absolutely so tiny that they can never flow to R values in the IR at our scales. So for a seven-brane gauge theory, the coupling is determined by the volume of the divisor that the seven-brane wraps. So 4 pi over G squared UV, G UV is the UV gauge coupling defined at the scale of compactification, is equal to the volume of the divisor it wraps, which is measured by the appropriate powers of the Kähler form on B, 1/2 integral J wedge J on D. And roughly speaking, we need this volume to be less than or equal to order 100, 25 to get the gut scale correct, which is not too large. And this will have some consequences for studying the corresponding effective field theory. So the reason being is that these n=1 theories are well behaved when the volumes of all cycles in the internal space B are greater than or equal to some order 1 number. This arises from the fact that the perturbative alpha prime curvature expansion is in 1 over volume, and the non-perturbative expansion is in e to the minus volume for volumes of various cycles in B. One pretty standard example is the corrections to the Kähler potential that come from worldsheet instantons wrapping curves in the internal space. And these corrections go as some infinite sum over the homology class of some curve, dn e to the minus 2 pi n times the volume. So n is just some integer, dn are roughly the number of such curves in that homology class in the base. And you can see if the volume of the curve is very small, well, these corrections will not be very suppressed, and they can spoil the validity of effective field theory. So generally, we want to make our all holomorphic cycle volumes of order 1. In fact, we probably want to make all cycle volumes non-holomorphic as well, at least of order 1 volume, but that's a discussion for another day. So in order to talk about volumes, let me introduce the Kähler cone and Mori cone. The Kähler cone is a set of all cohomology classes of Kähler forms on the space. These Kähler forms, remember, measure holomorphic cycle volumes. The Mori cone is the cone generated by effective curves, or 1D subvarieties in the space. These are holomorphic curves, and these two things are dual. All Kähler forms are such that they measure volumes greater than or equal, or that should say greater than 0, for all holomorphic curves in the base. So let me write down CA as a set of generators of the Mori cone, really of the semi-group of holomorphic curves in B. Well, if I then require integral over C of the Kähler form, C is a curve, is greater than 2 pi squared alpha prime lambda, lambda some order 1 number. Well, this implies the worldsheet instanton actions SW, SI are greater than some 2 pi times that same lambda. So by taking lambda bigger, I can help suppress the effects of these worldsheet instantons. I'll take the string length equal to 1, which means setting 2 pi squared alpha prime is equal to 1. And let me define this region of control, or region of, it's a proxy for region of control, called the stretch Kähler cone, which is the region, the set of Kähler forms J, such that the volume of all holomorphic curves is greater than or equal to 1. So I'm defining the stretch Kähler cone. Probably should have a tilde over there. So it looks something like this. If I have the Kähler cone here, and the Mori cone generator is defined by these walls here, where curves shrink down to 0 volume, the stretch Kähler cone is this region at least distance 1 away from all the walls, where all holomorphic curves have volume at least 1. The logic of defining such a thing is it's hard to compute the perturbative corrections as functions in the moduli, but we know when an effective curve is small, we can have an unsuppressed worldsheet instanton. So we're going to use the stretch Kähler cone as a proxy for control over the alpha prime expansion. It's not necessarily good enough, but it seems like a necessary condition, at least for most curves.
So Cody, that sounds strange to me. So you want perturbative corrections to be less important than this particular worldsheet instanton?
No, I want all corrections to be small.
Yeah,
and
this controls all size corrections, right? He's like taking all scales to be sufficiently big.
That's what I'm attempting to do, and the reason I made this distinction is just I can easily see what's happening in the worldsheet sum, at least from the parent n equals 2 theory, and how things can break down. The point of bullet point 1 is that it's just sometimes a little harder to compute the functional form of the perturbative corrections and understand when they're controlled. So I'm using I'm sort of motivating this using the non-perturbative effects. But I'm not trying to compare the size of the two. I'm just saying, let's make all curve volumes greater than 1 as a necessary condition to suppress the worldsheet instantons.
Okay, good. Okay, that's good. You basically need all volumes large for an F theory analysis to make sense, basically.
Yeah, and I'm doing the minimal thing. I'm saying all volumes have to be at least 1. That's not too big, but it's already going to have some consequences.
Okay.
And the key observation that I think underlies these consequences is that when the Hodge number of the base is large, so when the number of effective cycles grows large, this condition of making all curve volumes at least order 1 volume implies that some curves and some divisors are enormous. This is due to the fact that a large H11, the Kähler cone, in fact, is very narrow compared to the positive orthant or the effective cone. And this is a result from work with Mehmet Demirtas, Liam McAllister, and Mike Stillman. Generically, as an aside, this implies an essentially massless axion when H11 is moderate to large, as long as the masses are generated by a superpotential. So if you thought your Kähler cone and your stretch Kähler cone looks something like this, it's really more like this, where this is an even more cartoonish version because it's even narrower than this. So what are the consequences of being in the stretch Kähler cone? Well, large H11, some of the toric divisors become very large. And since the anti-canonical divisor is a sum over all toric divisors, that should be positive, the volume of such an anti-canonical divisor will be very large, the stretch Kähler cone, which is in conflict with achieving a realistic UV gauge coupling. So let's see how small we can make the volumes of these anti-canonical divisors while still remaining inside the stretch Kähler cone. So here's the problem that we want to solve at this point. Let's fix a base, smooth, weak Fano.
Wait, sorry, can you go back to make sure I understand? You're saying that the gauge coupling will be too small as a consequence of this condition in general?
Gauge coupling in the UV will be too small, that's right.
I see. So there's a tension between hitting a realistic value of the gauge coupling and maintaining sort of geometric control of the discussion, basically.
Yeah, exactly.
Mm-hmm.
Yep, that's the exact tension.
Okay, thank you.
So the problem, well, we're just going to take this anti-canonical class and we're going to try to minimize its volume with a fixed base while keeping all the volumes of all cycles greater than or equal to 1. And we're going to do this. I'm going to take one triangulation of each polytope to start and do this for all of those geometries. So the target volume, say if I want to hit the gut coupling, is 25. This is a log plot of these minimum volumes. And I've denoted this with a red line. So I want to hit 25. The bulk of the distribution is already is about 1,000. So this is already a problem. Let's see what's happening with as we scale up H11. Well, these black lines indicate where all geometries for one triangulation per polytope. So we have each one geometry per polytope. I don't consider all triangulations at this point. I have lines where all geometries at fixed H11 lie to the right of. So all geometries, the H11 equals 5, well, the min volumes of such their corresponding anti-canonical divisors lie to the right here. So at 10, we're already well outside the regime of realistic gauge coupling. Maybe not well outside, but at 15, we're hitting 1,000. And at 20 and at 25, we're quite far away. We're at 10 to the 4th, 10 to the 5. And for H1 equals 35 over here, we end up being around 10 to the 6th. So we're very far away from our target volume of 25. And remember that this was one triangulation per polytope, and an overwhelming majority of the geometries lie at H11 of B is greater than 15. Most of them are at H1 equals 35, but there's still quite a few at still large Hodge numbers. So virtually all geometries have volumes of the anti-canonical divisor that are much too large, and correspondingly, the UV gauge couplings are much too small. This was one triangulation per polytope. So we might ask what happens. Well, let's consider more triangulations. So about h11 equals 6 is where we hit 25. And for h11 is less than or equal to 6, well, we can just enumerate all the different triangulations we have, all the different geometries. And we have about 4,500 geometries below h1 equals 6. On the other hand, up here at h1 equals 35, we have order 10 to the 15. So it seems that a fraction of about 10 to the minus 11 of these geometries produce realistic UV gauge couplings in the regime of control in the stretch-Kähler cone. So the bulk of geometries lie at large h11, but the stretch-Kähler cone constraints push the gauge coupling to unrealistically small values. So if we want to wrap the standard model branes on this anti-canonical divisor, which allowed us to avoid dark gauge sectors, well, we have to make a choice. We either have to violate the stretch-Kähler cone condition, so violate this notion of control that we have in the alpha prime expansion, or choose a small h11 compactification, which is very, very non-generic. Of course, instead, one could do something different, which is to wrap standard model branes on a small divisor at the cost of introducing dark 7-brane gauge sectors. So let me repeat our claim. In a string theoretical realization of the standard model, the following 3 statements cannot all be simultaneously true. 1, our vacuum is a typical vacuum of the string landscape, which to me means moderate to large h11. 2, we're in a regime of control. The alpha prime expansion from string theory is controlled, which technically what I mean is that we're in the stretch-Kähler cone. 3, there are no additional dark gauge sectors, which technically what I mean is no additional 7-brane gauge sectors. And this all followed from trying to get the standard model gauge couplings correct. So let me just conclude with a few slides about what I think the possible consequences of this. Let's assume, probably a bad assumption, but let's just make the assumption for a second that the stretch-Kähler cone satisfying theories are representative, which, Clay, as you were pointing out at the beginning of the talk, is probably not a good assumption. But let's explore for a minute. What we would expect.
I don't know if it's good or not good. I just mean that it's uncontrolled. We don't really know.
Good. Yeah. No. That certainly yes. Then what we should expect is that there's a hierarchy of axion mass scales from this hierarchy of volumes, and possibly ultralight axions if their masses are generated by a superpotential. Also, we expect many dark gauge sectors with hierarchies of UV gauge couplings. Other things to look for are enhanced ALP photon couplings, which I explored in a paper with Jim, Gustavo Salinas, and Brent, which was fun, and asymmetric axion reheating in such models. But let's try to push beyond this a little bit. Let's see what happens when we get a little out of control. So part of the story is one of control. We want to know what's true in string theory, so we look where we can check. But this runs the obvious risk of a lamppost effect. So it seems that a majority of the possible standard models with the correct gauge couplings might appear at small volume where the alpha prime expansion is not controlled. So what can we say about them? Here on this slide, I will maybe wildly speculate a little bit of just things that, not that I necessarily think are going to happen, but what one might look for outside this regime of control. One might expect more intricate moduli stabilization scenarios that simultaneously evolve many instantons, because outside this regime of control, the instanton expansion is not suppressed. One also might expect heavier axions and dark sectors in strongly coupled physics, and frustrated bubble nucleation cosmologies due to very complicated potentials with many instantons that change the behavior of tunneling between vacua. Hard to check with current tools, but these are all important problems. So we might attack these with dualities, hints from the lattice, new tools, or toy models with enhanced SUSY. Perhaps a little less speculative is if we're at small volume, we expect a high string scale. So if we could somehow determine there were no or few dark gauge sectors in our universe and no nearly massless axions, this might imply that our universe has a high string scale. And I think it's very interesting to keep exploring these ideas. Thanks a lot. This is very fun. Really appreciate it.
But you can't see me.
Cody.
Yeah, the clap emojis.
Oh yeah, there is a, yeah, there you go.
There is a clap emoji, yeah. But I'm too lazy to press that. I'll just tell you in words. It's like
It's a lot of effort.
It's a passive aggressive clap.
Yeah, I'm clapping.
Yeah.
I have a couple of questions, but let me first see if other people have questions.
So can I have one question. So for you, dark sector means just something else, right? So what is the coupling between dark sector and the standard model?
Yeah, so to me, for the purposes of this talk, this meant dark gauge sector. So some gauge group somewhere. I didn't specify couplings. It could come from models where there is some direct communication, such as some charge matter between both gauge groups, or it could be gravitationally coupled. I wasn't specific.
From your constructions, you don't have any constraints on those coupling.
Well, actually, if I go back to some of the graphs I showed, where you try to tune something somewhere and you end up with a lot of different seven branes very nearby on the graph, those lines indicated intersections between the seven branes, which could support jointly charged matter. So there's some of this data is encoded in it, and it would be an interesting thing to study, but I haven't looked at it in any detail.
Okay.
But for instance, you could have, if you worked hard, tuned yourself to only permitting dark sectors that couple only gravitationally by forbidding such intersections if you wanted to.
Yes, that can certainly happen. Though for the small homology classes, that's not what you find. You have to work a little harder for that too.
Yeah. No, I don't mean that it's easy to find it. I just mean that it's a condition that you could easily impose in this framework.
Definitely. And that actually might be something interesting to study on its own.
Well, you need to, presumably at some point, you need to produce them for them to have any consequences, right? So if it's only gravitational, I don't know how you, well, I don't know. Yeah, so.
Well, maybe you could comment about that, Lian Tao. Are you implying that that dark sectors that only couple to the standard model gravitationally are basically harmless?
Depends on if you don't reheat to them, though, you don't produce them. They might as well don't exist.
Let me quickly also make a comment from the stringy point of view. That if you arrange for an axion reheaton that you attempt to couple to one of these single seven brane sectors, in the study that we did, which was in a similar ensemble, working in the regime of control, what you end up doing is you end up preferentially or asymmetrically reheating that divisor you attempted to reheat, but you also reheat the ones next to it, connected to it, at least a little bit. But you also tend to not reheat everyone else zero. They tend to get at least a little bit of energy dumped into them, but I can't quote off the top of my head what we found for that ratio.
Yeah, so in that kind of scenario, then you will have constraints, ineffective and so on, but it needs to have some coupling, right? So you have an axion, okay, that's fine, and then it means it couples, right? So to the inflation and so on. Right? You have to do something. So there's something has to be said. It's not just a basic gravitational coupling, then that doesn't do anything.
Oh, good. Yeah, thank you. That's a very good point. Yeah, there's always, I didn't talk about it much, but in these setups, there's always axions which can communicate between the sectors.
Okay. Yeah. Then it depends on the decay constant. So then okay.
Yeah. Thanks. That's a great question.
So Cody, so the main constraint is the classical gauge couplings are too small in a number of these geometries. If the classical, did you check how big the threshold corrections might be to the gauge couplings? Could they matter here in relaxing that constraint?
I don't think so, because the constraint came from getting the gauge couplings in UV much too small. And so I don't expect large corrections to this.
So the one loop, so because there should be sort of a relatively universal one loop threshold correction, which normally I guess it wouldn't matter, but because your classical coupling is so small, maybe it matters. Not sure.
Yeah, that's something to think about a little bit. I don't think it does, but yeah, I need to. Yeah, that's something to think about. Thanks, Lev.
I have one other question about the technology you're using to build and enumerate all of these elliptic Calabi-Yau geometries. Is there anything there that's intrinsically Calabi-Yau? Like if I ask the same question for Kähler-Einstein or other spaces that I could construct, even torically, say, could you come up with a similar count or estimate of the number of such spaces?
Yeah. So what you need to let me tell you how we do it here, and then we can try to think about how you generalize that. What we do is we start with a model that we understand very well, a base over which the Calabi-Yau elliptic vibration is smooth. So we know the M theory or F theory convectification on it makes sense. And then we make moves, which might be violent topologically, but we know have been proven to be within finite distance and moduli space. And since moduli space is just changing the vebs of fields, we expect the theories we get after that transition to still be well-behaved. And often we can understand the well-behaved, these additional theories directly anyways from seven-branes, intersecting seven-branes. So if you wanted to get to a new space, it sort of depends what you mean by new space. If you want to get to a new space with different Hodge numbers that's topologically distinct, we'd have to understand the corresponding topological transition and how that fits in physically to the theory we're working with. I don't know the answer for.
Okay. Yeah, no, I was thinking if you started with something that was not Calabi-Yau, but was Kähler-Einstein, say instead with say C1 positive.
Yeah.
I guess it will be a question of asking the same set of questions. To what extent are the topological transitions well understood, and can you explore, geometries that you can access that way?
Yeah, exactly. And there'd have to be results on distance and moduli space, and or the appropriate rephrasing of those terms, which is an extremely interesting question. I don't know the answer.
Yeah.
Well, I guess what's doing a lot of work here for you is this statement that all elliptic fourfolds are connected by birational transformations, which I think nothing like that is known outside of this class of geometries.
Yeah, that's definitely doing a lot of heavy lifting for us.
Do you know, by the way, just as a curiosity about that mathematical result, is it particular to fourfolds or is it known more generally?
Gross proved it for three folds in the 90s, I think.
Yeah. No, that one I know, but I didn't know about
Yeah.
the generalization to fourfolds, and I wondered if it was only about fourfolds or if it was more general than that.
If memory serves, it's four folds, but I'll have to look it up.
Okay.
Any further questions?
So what are you doing next?
That's a great question. Along these lines, or just in general?
Well, I more meant sort of along these lines, but you're free to answer it however you like.
Yeah, no. So, we're still, in these sort of ensembles, we're still trying to explore some of the phenomenological consequences of taking these ensembles seriously. So one thing we're doing is trying to understand the possible spectrum of gravitational waves from these dark gauge sectors, which tend to not have very much matter and will condense at some scale. So that's been particularly fun. Other things that we're interested in is trying to, in models with more supersymmetry, try to maybe understand things a little bit better outside the stretch Kähler cone and see if there's anything we can learn or extrapolate. Try to see if there's something like a minimum of some quantum volume somewhere in moduli space that might set the string scale. Other things that are quite interesting in these ensembles or related to it are understanding bubble nucleation cosmologies on these and how vacuum selection might be altered by the graph structure of the string vacua. So these are just a few of the many things that are fun to explore in this context.
Okay, great.
Yeah, thanks. That's a fun question.
Right.
Yeah, it's It's a easy one, softball.
All right, Cody, thank you so much. I'm going to stop the recording here.